vibrant tactile effects on response to footsteps. His work on the ultra-video conferencing system was recognized by an award for most innovative use of new technology from ACM, IEEE Supercomputing, and distinctly award from the Audio Engineering Society. Jeremy.
You changed my name.
All right. He here on the last name, so I need to remember the first name. Don't want to say Cooperstock. So Jeremy has worked with IBM, the Haifa Research Center Israel, and the Thomas Watson Research Center in Yorktown Heights, New York, and with the Sony Computer Science Lab in Tokyo, Japan. He also was the visiting professor at Plant Controls in Denmark. He conducted research on telepresence technologies as part of the World Opera project. He chaired the Audio Engineering Society Technical Committee on Network Audio Systems from 2001 to 2009 and is currently an associate editor of the Journal of the AES.
Thank you, Michael. Thank you, everybody, for coming to this tutorial. I will hopefully entertain you as well as inform you with a series of video clips to illustrate some of the examples that I intend to show to highlight the technologies that we discussed here. So, revolutions in human-device interaction. What is the sort of impact of this in terms of people with interest in consumer electronics, in terms of design, and in terms of the future of our technologies that are going to shape the world around us? What I'd like to start with is perhaps just asking the audience here to choose a technology. Pick a consumer electronics device that you use frequently today. And put it in your head, whatever, and ask yourself, how much cognitive effort, how much brain power does it take you to use it? How much attention do you devote to that device when you interact with it? Does it frustrate you? Does it get out of the way and let you accomplish your task easily? Do you make mistakes with it? Do you have to go back and repeat? Hands up if it ever causes you trouble. Wow, so about half of you don't. So those who didn't put up their hands, how about the gentleman over there? What's a consumer electronics device that you use that you don't find at all frustrating and that never causes you trouble? And that doesn't require huge amounts of cognitive effort to make use of? The iPhone? iPhone current generation? Or older iPhone? Do you use Siri? A little bit. So before Siri, the iPhone was flawless, never had any trouble with it. Typing mistakes, never any errors entering text. Minor issues. And that's okay. So we tend to be, especially the kind of crowd that comes to these conferences, we tend to be, although sometimes a little bit bothered by or a little bit distracted by the technology around us, we tend to view it as minor problems. It's like, well, I tried to type this whole sentence and I had to retype 20 of the words in it. A minor problem. I'm perhaps exaggerating for the sake of making a point here. But the reality is that for most people around, there are great benefits from devices like the iPhone, but also tremendous frustration. Why can't it be so much better? And in fact, with speech recognition like we have with Siri, of course it has become significantly better for the mainstream. That is, it's become usable in a more natural manner, okay? Where you can talk to the device and say, you know, add to my calendar the fact that my dad's birthday is next Tuesday, and it'll do it for you, using natural language, where you don't have to repeat every third word or worry about making multiple mistakes. And that's an illustration of how in recent years, and in the coming few years, the landscape is changing dramatically. So, going back a few, Mark Weiser, who was the father of ubiquitous computing, also the chief scientist or the director of Xerox PARC for many years, wrote a seminal article in the Communications of the ACM that described the field of ubiquitous computing. And his observation that motivated this was to comment that computers which we work, and thus disappearing from our awareness, they too often remain the focus of attention. That is, unlike a hammer that you pick up to hit nails into a piece of wood, and you forget about the fact that you're using a hammer becomes an extension of your arm. When we use computers or a consumer electronics device, our attention is focused on the device itself. And we might say, well, that's necessary because of the rich functionality and all the power. But the trade-off is that we end up getting distracted by it. And because of all that load of functionality and the complexity associated with it, we're more likely to make mistakes, we're more likely to forget how to do something, we're more likely to get frustrated. And the future, the revolution in the technologies hold that this need not be the case. So the flip side comes, not surprisingly perhaps, from the games industry. And we think about games and consumer electronics. Somebody famously said that the game industry created the consumer computer industry. And that individual is Nolan Bushnell, who was an inductee not so many years ago of the Consumer Electronics Association Hall of Fame. So Bushnell argues that games are easily the biggest driver of technological advances in this industry. And importantly, they're transformative. They're a transformative influence in the way we interact with technologies around us. Think about computer graphics. Think about displays, audio interfaces, input devices, multimodal interaction. All of these, if not invented to satisfy the needs of games, were enabled by the gaming industry. The drive for mass production, low-cost components, and so forth allowed for us to reach a level we have today. Now, there are two dates I would point out as being seminal in the sort of revolution that's already transpired. 2006 with the Wii, the Nintendo Wii, gaming side, and going back to the iPhone, 2010 with Siri. Not to say that speech recognition wasn't around before, but it became popularized at the mass level in consumer electronics devices just 2.5 years ago. So this tutorial, or the remaining part of this tutorial, is going to try to focus on these topics. And specifically, the fact that human-device interaction is becoming more natural, that user interfaces in turn are becoming invisible, achieving the sort of goals of Weiser's ubiquitous computing, to the point where we no longer have to think about them. The example of Siri, of course. And that we can use speech and natural gestures. We can benefit from geospatial aware devices. We can interact in 3D, exploit haptics, and experience multimodal augmented reality to enrich our lives and to better use the services and the tools around us. So what I'll try to do is highlight some of these technologies, some of these advances, some of the trends towards the future, and talk about the impact they may have on user experience. So first, the topic of gestural interaction sensing. With the introduction of the Wii in 2006, we saw an initial revolution, as I mentioned before, in the way users could interact in a more compelling, natural manner with computer-based devices. This is an example from a class project we did just a year after the Wiimote was introduced, where we looked at gaming experiences and showed how dramatically you could change it in just a few weeks of student time. So here's the example where the student's going to navigate a maze. Twisting the hand to open the door. So the Wii, and more recently the Kinect, brought powerful sensing technologies previously affordable only to a select few to the realm of the consumer. But the applications of these technologies are not limited only to tracking large-scale body motions like you saw in that video. They apply, moreover, to everyday interaction. They apply to facial expression tracking, as you'll see in just a moment. And of course, the Kinect has taken it a step further than the Wii in providing for sort of fully detailed video and the 3D depth sensing as well that the Nintendo did not provide. So here's an example where you're going beyond gesture of body and arms and dealing with gesture at the facial expression level. This is work out of EPFL in Switzerland.
With facial, you can slip into the role of your favorite 3D character. It's based on technology that allows you to drive your virtual avatar with your own facial expressions in real time. The software captures your facial expressions, analyzes them, and animates the virtual avatar. But currently, in online worlds such as World of Warcraft or Second Life, people can interact by chatting, by typing, by audio. But we really used to interact with other people face to face, to have emotion and expressions in the communication. And with facial, you can exactly do this. You can take the role of your character and have engaging communication with your peers. So the user just sits in front of a 3D camera, for example, that's the Microsoft Kinect, and the software will then track all facial expressions, the head pose, and the eye gaze, and that will onto the virtual avatars. Our first commercial product is Facial Studio, which is targeted at professional animators and artists to use them for the animations in games, movies, and TV. So we really provide real-time motion capture at every time. The basic principle behind the technology is that we take as input the 3D depth and color data that we get from the camera, and then we have a 3D model, a representation, a personalized avatar of the actor, and we basically find the best combination of expressions so that it fits to the depth and color data. And once we fit these expressions that you can see here over time, we can map these onto our virtual avatar. So we are really awaiting the next generation of 3D cameras, because more accurate and faster cameras means also even more astonishing results. And in the meantime, we will develop a software development kit that allows other developers to integrate our technology into their own products for online games, for Skype applications. And we really believe that this will change the way that people interact in online worlds.
Okay. Now, here's a related experimental technology that doesn't require the sensor to be placed on a table such that it can see the user at all times. This is something that just requires that you carry a small sensor device with you in your pocket, in your backpack, wherever it may be, and it picks up the electromagnetic signal of radiation around you from power lines, lighting sources, and so forth, and uses that to determine what gestures you're applying. It's not quite ready for prime-time usage yet, but you can see from the example how it can be used.
Human antenna. The system uses the body as an antenna for real-time, whole-body interactions. Human antenna senses full-body gestures without any instrumentation to the user, minimal instrumentation to the user. We leverage the existing electromagnetic noise coming from the power lines and appliances. Acting as an antenna, the human body receives this noise, which we use as our signal. By measuring the voltage over time at one location on the surface of the body, we are able to classify which gesture the user is performing. In previous work, we showed that this technique can be used to robustly classify a user's touch positions on walls and household appliances. In this work, we demonstrate the ability to classify free space gestures. In this demonstration, the system classifies the user's gesture and then animates a stick figure to mirror the gesture back to the user. This demo shows a user interacting with the Tetris game in real time. The applications of Human Antenna are not limited to gaming. Human Antenna provides a general purpose approach for user input in a variety of systems. Furthermore, Human Antenna can classify the location of the user in addition to the gestures being performed. This location and user information can enable a variety of context-aware, ubiquitous computing applications.
Now, here's another example where you don't even have to carry a device as a sensor, but just using the sound that's emitted from your speakers and picked up by the microphone, which could be in a handheld mobile device as well.
Gestures are becoming an increasingly popular means of interacting with computers. However, it is still relatively costly to deploy robust gesture recognition sensors in existing mobile platforms. Soundwave is a real-time sensing technique that leverages a speaker and a microphone to robustly sense in-ear gestures and motion around a device. It is capable of detecting a variety of gestures and can directly control existing applications without requiring the user to wear any special sensors on their body. To sense motion, this technique uses the Doppler effect, which describes the change in frequency as a result of relative motion between the sound source and an observer. Soundwave uses existing speakers on a device to produce inaudible tones of frequency between 18 to 22 kilohertz. Our system then uses the microphone on the same device to pick up the frequency shifted signal to recognize the gesture. Here we see the tone produced by Soundwave and the shift in frequency around it as the user moves his hand closer and farther from the PC. As the hand moves faster, the change in frequency is also greater. Variety of gestures can be realized by measuring characteristics of the sense signal such as speed, amplitude, direction, and time variation. By combining direction of the motion and its variation over time, the user in this example can change the direction of scroll by performing a double tap gesture. Using the number of motion events generated by Soundwave, walking towards or away from the laptop can be uniquely detected. In this example, it is used to lock the user's computer screen as he walks away. Soundwave is robust to audible sounds. For example, music can be playing on the same device as Soundwave is running on without affecting its sensing capabilities. This example application also demonstrates the use of two-hand gesturing. Here we see a user playing a game of Tetris by performing different gestures. Slow tapping gestures are used to move blocks left, while faster taps towards the right. Two-handed gestures are used to flip, and pulling the hand back in a quick stroke drops the block. This example demonstrates the accurate and quick control that Soundwave is capable of. To establish the robustness and reliability of Soundwave, we tested it in a busy and noisy environment.
Now, of course, that's a little bit limited in terms of the gestural vocabulary that you can express. It's a little bit of tapping and waving, basically much like a mouse. And we would prefer, perhaps, to think about a future where we have richer, more expressive types of gesture. Fortunately, the devices and the technologies that support that are always becoming more compact, more powerful, and less expensive. The latest, as you may have seen walking around CES the past week, is the Leap, which is just about to be introduced as a commercial product in Q1 of this year. This is basically the Kinect on steroids, but in a much smaller package. Look at what it can do. So the Leap is reported to have accuracy of 1/100th of a millimeter over a workspace of 2 by 2 by 2 feet. And that's pretty amazing. And uses a few VG VGA cameras built into that tiny little box. Now imagine that shrinking down over time, so that you've got that technology built into your smartphone, or built into your shirt pocket, whatever it is around you. Think about the capabilities of gestural expression and tracking, where your 10 fingers, your arms, your body is all being tracked with that precision. The subtleties of expression being recognized by the computer, what can you do? So with this trend continuing, with all of that expressive power, we're seeing where the point where multi-touch touchscreens are going to become a thing of the past. And we're going to view them as archaic and limited and constraining. Who needs a touchscreen? Yeah, that's what my grandfather would use. I mean, seriously, we're talking about interacting with 3D gestures that are recognized far more accurately than the best touchscreen, and that deal with all of the richness of the hands working together, not just with a few points, but actually shaping things and sculpting and so forth. Buttons, for example, buttons and dials that we have on physical devices are also likely to become a thing of the past because they're so limited. And the cost of recognizing all that you can do with a few cameras built into a small device will easily surpass and supplant all of the things that we do today with physical controls. Now, there's the haptics element as well. We'll come to that later. So what I'd like to do now is talk about a second class of technologies, which are the geospatially aware and the augmented reality class of technologies. Gesture sensing, of course, itself is very exciting, and the applications we've seen go well beyond that of gaming. But when we integrate gestures with the knowledge of spatial context, and we use augmented reality displays, for example, we can dramatically change not just the fundamental nature of the interaction, but our understanding of the world around us. What it means to use a device. So here's a nice example. I had the fortune of sitting on the PhD committee of the student who put this together. Think about the scenario where you've been using a 3-in-1 multifunction copier, scanner, fax machine. You're used to the controls, you're familiar with the instruction manual, you've actually read it, and it breaks down. So you go over to your local Best Buy or whatever the store where you buy your electronics is, and you go to buy the replacement, but the replacement now that's on special is from a different company. And it's got a completely different user interface. And oh god, I don't want to have to learn to use that. Well, here, using augmented reality, the work of Alexander Plouznikoff showed how you could replace the physical buttons and control panel of an existing interface, that is the physical device that he purchased, with a familiar interface from a previous system that is codified in software. You use a head-mounted display, a little bit awkward for current generation of consumer electronics, but I think it points towards the future. So here's a video of the interaction, turning an Epson multi-function device into a Canon equivalent. So the inset picture-in-picture shows what is going on in the physical world, and the display you see there is the graphical overlay. If it's playing, there we go. So the user is not actually pressing on any buttons, he's just doing this in the air near the device. But it looks to him as if he's pressing the buttons. And the display responds, it's all translated from what the system is telling it. Now, this doesn't necessarily buy you anything when your interface is already purely digital. You think about your touchscreen on your smartphone, you don't need this, right? You can regenerate the controls, you can regenerate the GUI anytime you want. But think about all the devices around us that are built on physical buttons and dials and sliders and so forth. Think about all the remote controls that are not digital screens but have buttons. And as you go from one device to the other, wouldn't it be nice to have the same interaction that you're already familiar with? So this is one of the ideas behind AR. And for those familiar with AR from not so many years ago, it was all based on the use of these sort of clunky 2D tags, AR tags or QR codes that we see ubiquitous around us today. But those aren't necessary anymore. You can have augmented reality with the everyday world, with any object around you serving as its own code. And you can even do more powerful things when you integrate projection. Here's an example that's done by a former student of mine, where he projects onto arbitrary surfaces and interacts with it using the same ideas behind AR. So really interesting here, seeing him transform everyday objects, like this sheet of paper or a cardboard backdrop, into a generic computer interface. So he's using an industrial camera and a small projector. And that's it. The projector is generating structured light to recognize the object on which...
Using IR camera?
No, regular camera. Yeah, yeah, using structured light to recognize the shapes. Now, in terms of the equipment there, of course, this is a laboratory setup. He's using a laboratory camera, a laboratory projector. But now, 2013, we have smartphones with built-in Pico projectors that are generating the output, that have the camera. You've got it all in one package. All of the technology you need to enable these kinds of applications already exists in a single bundle. Okay? You don't need to worry about where is your display. It's anywhere you've got a surface. Now, as far as where AR is heading, coupled with geospatial awareness, well, HP envisioned a possible future some years ago, something far more engaging than Junaio and Layar in terms of what you can do with overlays of kind of the video camera scene of a view of the world. This is something they created to sort of showcase one of their projects, and I like using it to illustrate where AR might lead. A little more engaging than looking at houses to purchase on the street. reality to substitute and superimpose different layers of content over the world around us has dramatic potential to change the way we view the world around us and our understanding of the objects. Here's a great example from Blaise Aguera, works at Microsoft and is doing the same thing with the Microsoft Maps as Google's done with theirs in terms of building this rich database of content from their cameras that drive around the world and map everything together. But here, interacting or integrating that content with photo collections from the crowdsourced public and showing what you can do in terms of stitching them together. It's really dramatic.
We've been working on a collaboration with our friends at Flickr. This takes Flickr georegistered imagery and uses photosynthetic processes to connect that imagery to our imagery. So I'm not sure if that's the one I actually meant to pull up, but notice this is of course a popular tourist site. There are lots of photos around here. And these photos are all taken at different times. So this one was taken around 5. So that's the Flickr photo. That's our imagery. So you really see how this kind of crowdsourced imagery is integrating in a very deep way into the map itself. Now, the reason this is interesting, thank you. There are several reasons why this is interesting, and one of them, of course, is time travel. I'm not going to show you some of the wonderful historic imagery in here. There's some with horses and carriages and so on as well. But what's cool about this is that not only is it augmenting this visual representation of the world with things that are coming in from users, but it also is the foundation for augmented reality, and that's something that I'll be showing you more of in just a moment. Now, I just made a transition indoors. That's also interesting. Okay, notice there's now a roof above us. We're inside the Pike Place Market, and this is something that we're able to do with a backpack camera. So we're now not only imaging in the street with this camera on tops of cars, but we're also imaging inside. And from here, we're able to do the same sorts of registration, not only of still images, but also of video. So this is something that we're now going to try for the first time live, and this is really, truly very frightening. Okay. All right, guys, are you there? All right, I'm hitting it. I'm punching play. I'm live. All right, there we go. So these are our friends in Pike Place Market. We're in the lab. And they're broadcasting this live. Okay, George, can you pan back over to the corner market, because I want to show points of interest. Yeah, no, the other way. yeah, back to the corner. I don't want to see you guys yet. Okay. Back to the corner. Okay, never mind. What I wanted to show you is these points of interest over here on top of the image, because what that gives you a sense of is the way, if you're actually on the spot, you can think about this. This is taking a step in addition to augmented reality.
So the computer vision behind this is fairly sophisticated, but it's no longer sort of rocket science. We know how to do this. But the power that this achieves is truly breathtaking. I mean, think about putting this technology in the hands of firefighters who need to see through the haze or the smoke or the fire to get inside a building that's alight. Or think of a disaster recovery person who's coming in after a building has collapsed in an earthquake and trying to find where the entrance used to be or where people might have been inside the building. Being able to superpose this live data from a video feed with the prior map registered contents is so dramatic in terms of its potential. It really is just a breathtakingly exciting application. And the possibility of now doing this sort of thing on our mobile consumer electronics platforms is dramatic. The previous examples that we've gone through, of course, are all very much focused on graphics and video, right? The display is a screen. You look at it. But we can do a lot of things as well with other modalities, such as audio. And here's an example where we want to deal with providing an environmental awareness capability for the visually impaired or the blind community. We want them to be able to understand what is around them, to visualize points of interest through leveraging the power of spatialized audio. So what we've done is taken, again, that same sort of geospatial data that exists in the Google Maps and the collections like OpenStreetMap, and encode that in a manner that is relative to GPS knowledge and compass knowledge available on the smartphone device, and represent that to the user in a manner that conveys to them the representation of their environment. Here's the example from a project we developed recently.
In-situ audio services, or ISIS, is an audio augmented reality application for blind users. ISIS lets you hear the restaurants, shops, and other points of interest as you walk down the street. This application is not meant to replace a cane or guide dog, but rather it is for exploration and discovery. Also, because blind users must be able to hear the real environment around them to navigate safely, we use headphones that don't cover the ears. Options include Mad Catz air drives or bone conduction headphones, both of which sit in front of the ears. To get the full effect, this demo is best heard through headphones, just as you'd be using for the application. ISIS is designed so that your device can sit in a carrier around your neck to keep your hands free for a cane or guide dog, as well as keeping the compass oriented in the direction you're facing. When you launch ISIS and hold the phone so that the screen is facing up, it is in stop and listen mode. Tap the screen once in this mode and you will hear your approximate address, which direction you are facing, how accurate the sensors are, and a summary of points of interest around you.
You are standing near 3535-3575 Arcade. You are facing southeast. Reported compass error 20 degrees. Reported location error 10 meters. Up to 70 meters in front of you are 2. Retail. 1. Other. 4. Restaurant.
Swiping a finger to the right on the screen moves forward through a list of locations ahead of you, while swiping to the left goes backwards through the list. When you're ready to go, you can let go of the phone and let it hang upside down in its carrier to enter walking mode. Walking mode automatically provides information about your surroundings while you're in motion. There are 2 options for walking mode. The first, radar, plays locations in a circle around you, while the other, shockwave, instead plays the closest ones first, then moves further away. When you let the phone hang vertically in its carrier around your neck, you'll hear a whoop noise to indicate that you've switched out of stop and listen mode, and it will announce continuous sweep to indicate that the radar will keep circling until you turn it off.
Continuous sweep.
If you lift the phone and lower it again, it will instead perform just one single sweep each time you tap the screen.
Single sweep.
As you walk, you'll hear the system name points of interest in a clockwise order around you. This is the radar sweep. You'll also hear a constant ticking to let you know in which direction the radar is pointing and to help reinforce the spatialization of the points of interest.
Other. Nitter Street Mart. Restaurant. El Gitano. El Gitano. Front left, 22 meters.
We've also implemented a second option for getting information while you walk called shockwave. Unlike radar, shockwave names the points of interest in front of you, starting with the closest places, then moves further away up to 70 meters. As the shockwave moves forward, ISIS ticks to let you know it is progressing, and also tells you when it sweeps past 20, 40, and 60 meters ahead of you. If you missed something or want to hear more details, place and hold a finger anywhere on the screen. ISIS will interrupt the radar or shockwave and give you more complete details, including distance and direction to the most recently played point of interest.
Quality Hotel downtown. Right, 28 meters.
Once you have your finger resting on the screen, you can also slide it to the left to get the details for previous points of interest.
Cafe. The Colo Espresso Bar. Front left, 14 meters. Building dining pageantry. Front left, 11 meters.
Since the compass and GPS aren't perfect, we'll also hear different ways in which the system describes locations. The default in all modes is for ISIS to tell you how many meters away something is from you, and whether it is right, left, ahead, or behind. But it may also tell you the location of a place by its relation to the closest intersection.
Second cup. 8 meters this side up. Intersection. Avenue, Park and Room, Milton.
Because even relatively small position errors due to the GPS can significantly alter the scene, ISIS will snap you to the nearest street, which, for example, helps to ensure that places render on the correct side. And if the compass error is high, then ISIS will fall back to cardinal directions, such as north, south, east, or west.
Alto Restaurant Incorporated. East, 40 meters.
The database we use for ISIS allows us to render not only the businesses and landmarks near you, but also intersections and bus stops. ISIS can also tell you whether you're inside or outside regions such as parks. If you are just interested in a single type of location, ISIS can also filter the points of interest to only include transportation, food, shopping, entertainment, or services. We also have ISIS working on a Galaxy Nexus phone running Android. If you have questions, please visit our website at isas.sim.mcgill.ca for more details. The ISIS project is funded primarily by the Secrétariat du Conseil du Trésor of Québec through its appui au passage à la Société de l'Information, with extensions supported by a Google Faculty Research Award.
So what's interesting with that is even though it was developed for the blind community, we find that visually capable users use it with gaining quite a bit of knowledge about the environment with which they might even already be familiar. I walked down streets just around my home and discovered all kinds of places I didn't know about because they were buried inside malls or upstairs on the second flight of a building. Think about the uses for tourists in a new city. You know, I don't know Las Vegas, walking down the streets here, I can get information conveyed to me, giving me data, giving me points of interest that might not be visible. Useful for drivers in a car situation where you're focused on the road, but you want to know about things that are beside you or off to a street or so behind the current location. This can be provided leveraging the power of the audio domain. We've covered, of course, the use of gesture sensing for recognizing input in 3D. And for those who've been walking around the CES for much of the past week, it's hard to avoid seeing 3D displays. There's the big LG entranceway to the exhibit area, massive 3D everywhere. But what about interacting with that content? What about engaging and getting our hands into 3D and actually engaging with it? So how might future consumer electronics let users engage with such 3D content? Let's look at a few possibilities. First, if we consider the fact that a display, even though today they're usually a single flat surface or possibly a slightly curved surface, a display doesn't have to be that. You could have displays at multiple angles covering every surface of a particular device or appliance. And once you have that, you can generate content that looks like it's inside the device. And you can then start to interact with it as you would naturally with a 3D object, with a real physical entity. Here's an example from colleagues.
PQB, a personal cubic display that arranges 5 flat panel screens into the shape of a box. By tracking both the user and PQB, we can render perspective corrected images and support tangible interactions, such as rolling and bouncing objects, navigating a large scene by tilting, and poking and prodding objects.
So those same possibilities extend to larger displays as well. You might think, well, larger displays, that's not the stuff of consumer electronics, but of course with with the projection world becoming integrated into smaller devices and increasingly affordable, it is possible to think about large displays being consumer appliances. So questions we talk about in terms of interacting with another human, a holographic representation, is no longer just the stuff of science fiction, but becomes a reality that we have to think about what are the paradigms of interaction when you have a virtual human inside your environment. And here's an example where we built a telehuman that provides for full stereoscopic and motion parallax display of a life-size human. I'll give you a little clip of what that looks like.
We present Telehuman, a life-size, cylindrical telepresence pod. Traditional flat displays often do not provide support for certain nonverbal cues in telepresence situations, specifically body pose, as well as eye gaze and pointing. With Telehuman, a user can walk 360 degrees around a live 3D representation of a remote participant and see them from all angles. Combined with a stereoscopic 3D projector, this creates the sensation that the remote participant is standing inside the display. Telehuman uses Microsoft Kinect sensors on top of the display to track user position. Custom distortions are used to project images off a hemispherical mirror, and a 3D projector is used to add stereo depth cues to the system. We evaluated how motion parallax and stereoscopic depth cues enable users to accurately identify where a remote participant was indicating when they used gaze, pointing, and the combination of pointing and gaze. Additionally, we evaluated users' ability to understand a remote participant's full body pose. Participants viewed poses demonstrated by a yoga instructor projected inside the display, and provided instructions on how to perform the pose to a co-located user.
So that's the large-scale example. But we're not limited to large. We can also take it down to small, mobile devices. We can achieve the same effects on commodity platforms that we use every day, treating these devices as if they're a virtual window, small little portal into a larger space. And you can manipulate it, panning it up and down, left, right. You can have hyper-realistic effects like exaggerated zoom by moving in and out. And you can move around a virtual scene as if you're holding a little kind of viewfinder into it. These kinds of displays, of course, can also be rendered in stereo. And we've seen lots and lots of examples in consumer electronics that are very affordable, that are used for gaming, almost always for gaming, some for viewing 3D content, sort of movie picture sort of things. Using an overlay that provides for glasses-free 3D, using autostereoscopic techniques, either parallax barrier or lenticular. And while the resolution is not as good as you get with the glasses type viewing, the point is it's portable, it's usable pretty much anywhere without having to don any special headgear. And that's quite compelling. We can also use the same 3D technologies, the 3D displays, for other purposes other than 3D. There's an example here. We developed a medical treatment for amblyopia, or lazy eye syndrome. The idea is to leverage that same technology to give differential information to the two eyes. The treatment theory is based on the fact that the people who suffer from lazy eye, the weak eye is actually possible to engage, that is to get the brain to pay attention to its signal if you provide it with a sufficiently high contrast. If the contrast ratio of the weak eye versus the good eye is imbalanced enough, the brain will pay attention to the two. And what we do is we give the two eyes complementary information, such that the user who's trying to play the game, in this case Tetris, has to actually see the information content in both eyes to play. If you cover one eye, you're not going to play the game well. And over time, we can gradually reduce the imbalance between the two eyes to try to approximate that of normal vision. And we've shown that even in adults, we can do that using the same technology. So, the final topic, before we get to the sort of combining a few together, is that of haptics. Danny insisted that we have a component here on haptics, and I'm happy to do so. Haptics for consumer electronics, though, means for me haptics for everyday objects. How do we build haptics into the world around us, into not specialized big apparatus or just relying on haptics being the vibration of the motor of the cell phone, but actually giving us richer feedback that conveys something of nuance about the world. So we've got the tools, we've got the building blocks available. Plethora of sensors, wide variety of actuators that can be used. These are largely small scale that integrate pretty much anywhere. So where do we go beyond the norm? Where do we go beyond just vibrating the cell phone? Well, here's an example. We worked on a project for a car company who wanted to build in rich situational environment awareness of the state of the car. Things like knowing what the volume level was or what the speed you were driving and so forth, without having to take your eyes, off the road. Right? So pay attention to where you're driving, but get information displays delivered through your hands. And be able to command, of course, the display of information by using gestures of the fingers. So we equipped a steering wheel with a flexible capacitive sense 2D sensor, and we display the output using actuators. These are vibrating voice coil type elements. Sorry, not voice coil, but what's the word? Drawing a blank on the technology. But these are elements that fire back and forth. No, it's not solenoid. Simeon's work. It's the principle.
They're linear resonant actuators.
Okay, thank you. I'm not a mechanical engineer. So these are mounted inside of the steering wheel base, and they deliver a fairly strong response to the hands. It can be felt all over the wheel, and they're controllable both in terms of the frequency and in the amplitude separately across the 2 dimensions, which is important if you want to convey rich vibrotactile feedback to the fingers. Another example here is Ravel. This was shown at SIGGRAPH last year, and it uses electrical fields to provide tactile feedback, again, on everyday objects as long as you're connected to the anode.
Current tactile technologies enhance objects and devices with various actuators to create rich tactile sensations. However, the tactile experience has been limited to the interaction with instrumented devices. We present Revel, a new wearable tactile technology that instead modifies the user's tactile perception of the physical world. It adds artificial tactile sensations to almost any surface or object, with very little, if any, instrumentation of the physical world. As a result, Revel can provide dynamic tactile sensations on touchscreens, but also on everyday objects and surfaces in the environment, such as furniture, walls, wooden and plastic objects, or even human skin. Revel utilizes a new tactile effect that we call reverse electrovibration. The Revel device injects an imperceptible electrical signal into the user's body. When touching a physical object covered with an electrode and insulator, an electrical potential difference between the finger and the electrode creates an electrostatic attraction force that modulates the friction between the sliding finger and the object. By varying the signal properties, such as the amplitude and frequency, different tactile sensations can be created. Both the object and the user must be connected to a common ground, either directly or capacitively. The Revel device generates arbitrary signals that can be applied anywhere on the user's body. For example, Revel can be embedded in the seat of a chair, in the handle of an umbrella, in the sole of a shoe, or in the casing of a touch device. Revel can add a layer of controllable tactile textures to a wide range of surfaces and objects. For example, it can provide tactile feedback both on a touch screen and the physical object itself. It can enhance large interactive touch surfaces with tactile feedback and also add textures to projected content on tables and walls. It can enhance painted objects and paintings with artificial tactile sensations, or even augment interactive display cases with textures related to their contents. Revel is mobile, wearable, and inexpensive. Therefore, it could be used in the future in many exciting applications. For example, a user wearing Revel could access private tactile information on public touch displays, experience personal tactile sensations in collaborative touch applications and games, and feel dynamic tactile feedback on posters and maps. It could also help users in everyday tasks, such as highlighting a sought object with a distinctive texture, or providing tactile direction hints to the visually impaired. The versatility of Revel enables the expansion of dynamic tactile feedback from interactive devices to anywhere in the physical world.
Now, back when I was talking about the leap and other forms of 3D sensing that are contactless, I made the point that maybe we want to get rid of all the buttons and dials and knobs around us because we can do so much more with 3D. But the reality is that touch still provides so much information that we're not quite ready to give up on it. It would be a shame, in fact, to lose out on the additional modality of information we can obtain. And here's a beautiful example that shows how augmenting or driving by computer a simple set of squeezable panels is something that could enrich significantly the quality of interactions with different devices.
Squeezeblock is a novel haptic feedback system that can change its elasticity to convey information in an ice-free interaction. It is an electromechanical system that implements a virtual spring. When a user squeezes the device, it feels as though there is a spring inside. In reality, it is software control, allowing us to change the perceived stiffness. We envision the squeezeblock technology in a mobile phone where, for example, the user feels the stiffness to infer the number of important unread messages while it is still in his or her pocket. With software-controlled elasticity, Squeezeblock can demonstrate various behaviors. The most basic of these is a linear spring. The user squeezes the device by applying force on the pressure plates, which deform in relation to the amount of force applied. The forces on the two pressure plates, as sensed by our system, are shown in the bottom left corner of the screen. As we change the K values, or stiffness of the spring, observe that the user must apply more force to deform the squeeze block. With the high K value, the squeeze block becomes nearly rigid. We can also change the length of the virtual spring by changing the range of deformation that squeeze block exhibits. Observe that increasing the allowable range of motion creates the illusion of larger spring lengths. Since the relationship between force and displacement is entirely implemented in the software-controlled system, we can implement complex functions such as those having discontinuities and multiple states. With the discontinuous function, the device behaves as a linear spring up to the discontinuity, which is then perceived as a click. The number of clicks, for example, can indicate the number of unread messages. Using a state machine, multiple force displacement functions can be combined into a single experience. Here we implement a two-state system to realize a parking brake-like behavior, which can also be used as an input gesture. For example, putting the device in a compressed state changes the ring profile of the side light.
So here you've got
changing size statically comes as a free feature of squeeze block. As an example application, the increase in size can indicate an upcoming appointment. squeeze block is housed in a custom-designed aluminum casing that was milled on a 3-axis machine. It consists of a motor, a shaft encoder, and a rack and pinion gear system, all governed by a microcontroller running at 16 megahertz. A software-implemented PID controller ensures accurate and fast positioning, which is crucial to creating the illusion of a spring.
So here you have a fairly simple mechanism. Waving goodbye. Fairly simple mechanism that could be added to almost any sort of consumer electronic appliance and provide for this input and output capability that is so controllable, so rich in terms of the types of display, with just simply 2 plates that you're interacting with. The range of buttons and sliders and so on, all enabled through that basic interaction. Gupta also developed a rotary sort of version, which he called the InGen, that provides both sensing and
interactive generator, or InGen, is a self-powered, general-purpose wireless controller capable of providing haptic feedback. The motivation behind InGen lies in how we interact with physical objects. In these, force feedback is a rich information source. Providing virtual objects with this type of feedback usually consumes considerable power. InGen is our solution to this power challenge. InGen is a rotary haptic device which powers its electronics, sets the direction and speed of the iteration, and presents its force feedback, all from the rotation of the device. Internally, InGen has 2 components, a DC motor and a circuit board. The DC motor is geared and modified to include a potentiometer. The motor's function is twofold. It provides the power for the device while presenting force feedback to the user. The circuit board is responsible for controlling the type of feedback, as well as communicating wirelessly with the host PC. InGen delivers 3 types of force feedback. First, InGen can generate resistive feedback, which changes how easily the device rotates. Changes in resistance can be triggered by user input. In this step, the resistance increases automatically as the device is rotating. Also, authorizing counterclockwise directions can be controlled independently. The second type of feedback, detents, feels similar to using a computer mouse's scroll wheel. Lastly, InGen can simulate mechanical stoppage, preventing the user from turning the device further. To demonstrate the potential of InGen as an input device, we created a simple television browsing and selection application.
And what I love about Gupta's videos is that unlike pretty much everything else you show in haptics, you actually do get a perception of what it feels like just watching the video. So it's really well done in production values there to get that across. So these are interesting examples where you're augmenting what would seem to be just a simple mechanical object, but endowing it with these rich sort of augmented computer capabilities of expression and using them as sensors at the same time. Taking it one step further is the work of Sato et al. On Touché, which deals with far richer kinds of sensing capabilities and applying that to everyday objects where you do want to have that physical grasp in order to provide your input. So this is sort of a trade-off of do we use the 3D touchless types of interaction that we have with something like the Kinect or the Leap, or do we actually want to have contact with the appliances and the devices in order to provide the input? So here's an example of what you can do with a physical object to do some of that rich kind of sensing of gesture.
Touché is a touch sensing approach based on swept frequency capacitive sensing. Conventional capacitive touch sensing operates at a single frequency, allowing for a single capacitive reading. This value goes up or down depending on if a finger is touching. This generally means capacitive touch sensing is binary. Either the user is touching or they are not. Touché, in contrast, sweeps over a range of frequencies, sampling the return voltage many times. This builds up a capacitive profile, which contains considerably more information. We can pass this to a recognition engine, enabling a wide variety of touch gestures. Our approach can be used to enhance both traditional touch interaction, for example on smartphones, and also make everyday objects and materials touch and gesture sensitive. To highlight the wide variety of applications Touche enables, we constructed 5 exemplary setups. In general, Touche requires only a single wire be connected to objects, as demonstrated here with a doorknob. 5 gestures are supported: no touch, 1-finger touch, 2-finger pinch, a circle gesture, and a grasp. Note how the capacitive profile changes in the background. Touche could also be implemented into a table, which could sense a user's posture or body configuration. It can even sense when no user is present. Touche also has great potential to enhance conventional touch sensing, which, as noted before, is traditionally binary. For demonstration, we created a pinching gesture set, which works in concert with regular 1-finger pointing. In addition to knowing when the user is touching and not touching, it can also sense when the user is pinching with 2, 3, or all 4 fingers. Touche does not require metallic objects, and can even add touch sensitivity to the human body. Our sensor board is wireless, communicating over Bluetooth to a computer or mobile device, enabling true mobility. Finally, Touche enables many unique opportunities for touch interaction. For example, we can add touch sensitivity to liquids easily with a single electrode located under the fish tank in this example setup. Body. It is not inconceivable that one day mobile devices could have no screens or buttons and rely exclusively on the body as the input surface. Touche could also be used to enhance current interactions with mobile devices. For example, the pinching gesture shown earlier can operate like alt-clicks for mobile device touchscreen. Here, a user alt-clicks on a file, which instead of opening the document, brings up a contextual menu with more options. It is also easy to imagine a smart doorknob that knows how it's being grasped, which in turn can trigger different functionality. Here, a user sets their status to Do Not Disturb. If on the phone or during a meeting, another gesture could set a Come in quietly message. How the user closes the door could also be used. Using a light 1-finger hook could set a Back in 5 minutes message, whereas using a more solid grasp sets the message to Gone for the day and simultaneously locks the door behind the user. Finally, in the home, we could imagine a sensing sofa. When the sofa detects a user sitting down, the TV could be turned on. As the user relaxes and lays back, the lights could dim automatically. Finally, as the user slips into sleep, the lights could be dimmed further and the TV turned off.
So with these examples, I've hopefully illustrated some of the design challenges and design questions that we would pose when trying to contemplate what is the right way to build a particular device, what is the right sort of interaction paradigm for the class of functions you're trying to enable, and how is it that users would more naturally relate to the range of functionality that you're trying to provide. As a final note, I want to try bringing together a few of the modalities and show you, this is a joke, the possibilities of multimodal immersion in a rich environment to engender to the user a perception of a different kind of environment that they're not actually physically in. This is work that we did several years ago, and we've augmented it recently with experience of water surfaces as well. I'll just let the video give you the storyline. So while this example is not necessarily a consumer electronics device or something we could imagine carrying with us, I think what it does is provide a sort of motivation for what might be the possibilities as we consider the richness of the sensing and actuation possibilities of some of the technologies that we've illustrated in the rest of the tutorial. And I hope this inspires designers in the crowd to think about next generation of devices and appliances and functionality that can be engendered from this rich capability. Thank you for your attention. If there are any questions, I think we have a bit of time left. I'm happy to elaborate. Yes, sir.
Has anyone addressed the fantasy of taking a USB smart stick and sticking it in a port in your body that would enable you to not only just see the data, kind of like when you came with the musics, the fact that you just see data is not exciting to me anymore. We know it's coming. It's more exciting to me to know that the tech can help us react better. Because when I tested the demos, I'm sure young kids will be better than I am at it, but when I tested the demos, you got to kind of look down, look, focus, and use your own attention. Whereas, I guess it's helping a little bit, but I feel like there's so much more by somehow integrating it into the nervous system or something like that.
Yeah, well, your question touches on several different facets of the way technology is heading in this regard. Some of it sounds borderline science fiction, but a lot of it is reality today. The two axes that I probably want to address in responding are the very rich levels of visual information that gets transmitted from our eyes, and to replace that effectively, basically having a pathway into the neural system to bypass the retina and give that same richness, we're nowhere close. Okay, I mean, that's just such a mass of nervous system and connectivity to the rest of the brain. We have no idea how to do that. There have been successes in stimulating groups of neurons through, for example, transcranial magnetic stimulation to induce sort of vague patterns, but nothing along the lines of actually being able, for example, to read text or recognize a picture. The other side of the answer deals not so much with the USB stick, but other kinds of sensing or sensor implantation into the body. The one example that comes to mind was, I think it was a British, I can't remember, he was a biophysicist or something, he was somewhat unrelated. He embedded into his arm, I think it was his wrist or somewhere lower palm. Now what was it? It was a RF or magnetic, it was a magnetic sensor. And by having this inside under his skin, as he would walk near power lines or throughout the city, the small vibration and motion of this magnetic sensor triggering from the electromagnetic fields gave him this extrasensory capability of understanding the fields around him. And after a few years, when he had an infection because of this implantation, and it came out, he felt as if he was almost blinded. He'd lost a part of his identity and who he was and how he sensed the world. Now, this is perhaps a bit of a far cry from what you're talking about of not having to focus on things, but I think it illustrates a little bit about how we're heading in terms of being able to bring technology into ourselves, into our bodies, whether it eventually goes straight into the brain or through other nervous pathways to give us that information. It's there, it's happening. Is it ever going to replace our actual sensory mechanisms for those who still have vision and audition and taste and so on? Or will it only be to add, for example, giving us pigeon view of the world in terms of the richer spectrum that they perceive the environment? I don't know. Does this have a role or a shape in terms of consumer electronics for the future? That's another question. But it's certainly something interesting to ponder.
Thank you.
there's nothing else, I'll bring it to a close and